Welcome to the Explainer. Today we're pulling back the curtain on one of the most brilliant pieces of software ever made, the invisible but totally essential machine that powers pretty much the entire Java universe, the JVM.
I mean, seriously, think about it for a second. You write a single piece of code, and it just works. On a Mac, on a Windows PC, on a Linux server, you name it. How is that even possible? Well, that kind of magic is no accident. It's an absolutely deliberate and brilliant piece of engineering.
And this leads us to this legendary phrase, which was the revolutionary promise of Java. The whole idea that you could build something one time and have it work perfectly on any device. The invention that makes this a reality? You guessed it, the Java virtual machine. So, let's go take a look under the hood.
So what exactly is this universal machine? Let's take a little tour and see how it all works, from the front door all the way to the engine room.
So, at its core, you can think of the JVM as this amazing middleman. Your code doesn't talk directly to your computer's guts, the hardware. Nope. Instead, it talks to the JVM, and the JVM acts as a translator, passing on the instructions to whatever specific machine it's running on. It's basically a universal translator that makes your code feel right at home, anywhere. All right, our tour kicks off at what you could call the loading dock. Before the JVM can do anything, it needs to get the raw materials, your compiled Java code, inside the machine. Now, this isn't a job for just one guy. The JVM has a specialized team called the Class Loader Subsystem. Think of it like a three-person crew. The Bootstrap loader is the heavy lifter, bringing in all the essential core Java parts. The extension loader handles any optional add-ons. And then the application loader, well, that one's in charge of loading your specific program.
But here's where it gets really, really smart. It's all about how this team works together. It uses something called the parent delegation model, and it's a fantastic security feature. See, when your app needs a class, its loader doesn't just grab it. First, it asks its parent, the extension loader, and that one asks its parent, the Bootstrap loader. This chain of command makes sure that a core Java class can never, ever be sneakily replaced by a malicious one from your application. The most trusted loader always gets first dibs.
Okay, the code is loaded. So, where does it all go? Let's step inside the JVM's workshop. This is where it meticulously organizes everything it needs into different memory areas to keep the whole operation running like clockwork. So inside, the JVM carves up its memory into a few key sections, often called the runtime data areas. And just so you know, this chart is just a concept. These sizes aren't fixed, they're always changing. You've got the method area for all the class data, the heap where all your objects get to live, the stack for method calls, and a couple others for general bookkeeping. Each one has a very specific and crucial job to do.
Now, let's zoom in on the two big ones you'll hear about all the time, the heap and the stack. The heap is like a giant shared factory floor. It's where all the objects and arrays for your program are built and stored, and it's accessible to everyone. The stack, on the other hand, is more like a private workbench for each individual worker or thread. It keeps track of temporary stuff and which method called which, making sure the work gets done in the right order. All right, the code's loaded, the workshop is all organized. Now for the fun part. Let's head down to the engine room and see how the JVM actually brings your code to life.
Down in the engine room, you've got this amazing two-person team. First up is the interpreter. It's all about speed at the start, reading your code and running it one line at a time. But for code that runs over and over again, these hotspots, the interpreter can be a bit slow. And that's where its partner, the just-in-time or JIT compiler, is a total hero. The JIT finds these hotspots and compiles them into super fast code that's native to the machine. This dynamic duo gives Java the best of both worlds, a fast start and incredible performance over the long run. It's the real secret to how Java can be so darn fast.
You know, any busy engine room is going to get messy, right? That's why the JVM has this awesome automated cleanup crew, the garbage collector. It just runs in the background, constantly looking for objects in the heap that nobody needs anymore. When it finds them, it automatically frees up that memory. For programmers, this is a lifesaver. It means you don't have to worry about manually cleaning up memory, which prevents a whole class of nasty bugs called memory leaks. It's a huge part of what makes Java so reliable.
Okay, so we've seen all the different departments of this incredible machine. Now let's put it all together and watch the entire assembly line work in perfect harmony. So here it is, the whole process from start to finish. First up, the class loader brings in the code. Then, that code gets verified to make sure it's safe and sound. Next, the JVM sets up all the memory it needs in the heap, stack, and other areas. Then, the execution engine, with its interpreter and JIT compiler, gets to work running the code. And all the while, the garbage collector is tirelessly working in the background to keep things tidy.
It's really like a beautifully coordinated dance.
And this entire architecture, from the secure way it loads code to the smart way it executes it, that's what makes Java's original promise of write once, run anywhere actually work. It is, without a doubt, the cornerstone of the language's legendary platform independence and its rock-solid security.
The JVM really is a masterpiece, an invisible engine that's been powering countless applications for decades. It kind of makes you think, doesn't it? What other amazing, foundational technologies are working silently behind the scenes, making our whole digital world possible? Something to chew on. Thanks for joining us on The Explainer.